So how do you make a smart decision when the future is, well, a total mystery? We face this all the time, right? In our jobs, in our lives. But here's the thing, there's actually a powerful toolkit for handling all that uncertainty. Today we're going to break down probability, not like some boring math class, but as a real, practical guide to making better bets. Let's dive in.
We've all been there, asking questions just like this. Every single day, we're trying to guess what's going to happen, trying to figure out the odds. And a lot of the time, it just feels like we're throwing darts in the dark. But what if it didn't have to be that way?
And in the world of business, the stakes get way, way higher. We're talking millions of dollars riding on whether you understand the chances of success. So how do we get past that simple gut feeling and start making a truly calculated risk?
Well, the answer is probability. This is the tool we use to actually put a number on uncertainty. Think of it like a scale. A 0 means there's no way, it's impossible. A 1 means it's a total lock, a sure thing. And everything else, all the maybes in life, falls somewhere in between. It's a common language we can all use to talk about chance.
Okay, so where do we even begin? Well, before we can figure out the odds of something happening, we have to get a handle on all the things that could possibly happen in the first place.
This complete set of every single possibility has a name. It's called the sample space. And it can start out super simple. You flip a coin. What can happen? Heads or tails? That's it. That's the entire sample space, the whole universe of possibilities for that one flip.
Right, but life is almost never that simple, is it? What happens when you're dealing with dozens, maybe even hundreds of different outcomes? Just trying to list them all out would be a nightmare. We need a smarter way to count.
And this brings us to two really important ideas, combinations and permutations. Now, they sound a little technical, but it all boils down to one simple question. Does the order matter? For combinations, the order absolutely does not matter. Picking part A, then part B is the exact same thing as picking B, then A. But for permutations, order is everything. Getting first place in a race is a whole different world from getting second.
All right, let's make this real. Imagine a quality check. An inspector needs to grab any 2 parts from a bin of 5. Since it doesn't matter which part they grab first or second, this is a combination. And if you do the math, you find out there are exactly 10 possible pairs they could pick. Not mine, not 11, 10. That's our total number of outcomes. But let's change just one tiny rule. What if the order does matter now? Let's say the first part chosen gets a super detailed inspection, and the second just gets a quick scan. All of a sudden, the number of possible outcomes doubles to 20. Why? Because now, part A, then part B, is a totally different outcome from part B, then part A. This just shows you how critical that one question, does order matter, really is to getting the right count. Okay, so now we have a handle on how to count all the possible outcomes. What's the next step? Well, now we have to figure out how to assign an actual probability, a number, to each of those outcomes.
And there are basically 3 ways to do this. You've got the classical method, which is perfect for things like a fair die roll, where every side has an equal shot. Then there's the subjective method, which is really just an educated guess based on expertise. But the one we use most in business is the relative frequency method. This is where we use data from the past to make predictions about the future. Let's see how that one works.
Here we go, a perfect real-world example. A clinic wanted to know how many patients were typically waiting at 9 a.m., so they tracked it for 20 days. You can see right there in the table, on 6 of those 20 days, there were exactly 2 patients waiting. So our best guess for the probability of that happening again is just 6 divided by 20, which is 0.30 or 30%. See? We're using what already happened to predict what's going to happen.
So far, we've kind of been looking at events as if they happen in a vacuum. But in the real world, things are all connected. The chance of one thing happening can totally change based on whether something else happened. This is called conditional probability. And this, my friends, is where things get really powerful. So check out this data. It's from a study on promotions for 1,200 police officers, and it's broken down by gender. Now, sure, we could just look at the overall promotion rate for everyone, but the really juicy questions come up when we start to see how these different categories affect each other. So let's ask a really specific question. We're not looking at all 1,200 officers anymore. We are adding a condition. We only care about the officers who are men. How does that single condition change the probability of being promoted? To figure this out, we just zoom in on the data. We totally ignore everyone else and focus only on the 960 male officers. The table shows us that out of those 960 men, 288 got promoted.
So you just take 288 divided by 960, and you get a conditional probability of 0.30. In other words, there's a 30% chance of promotion if you're a man in this dataset. Okay, you know what's coming next. Let's ask the exact same question, but for the other group. What is the probability of promotion given that the officer is a woman?
We run the same play. We zoom in again, but this time we're only looking at the 240 female officers. Of that group, 36 were promoted. So 36 divided by 240 gives us 0.15, only 15%. Now hold on, look at that. The probability for men was 30%, but for women, it's half that, at 15%. Because those numbers are different, we've just proved that in this data, promotion and gender are dependent events. One clearly affects the chances of the other.
This whole idea leads us straight to our final and maybe most powerful tool. What happens when you have an initial belief about something, but then you get a new piece of information? Well, you update your belief, right? And the formal, mathematical way to do that is with something called Bayes' theorem.
Now please don't let the name scare you. All Bayes' theorem really does is give us a logical way to revise our probabilities as we learn new stuff. Let's say we find a bad part on an assembly line. We know it had to come from one of two suppliers. Bayes' theorem helps us figure out who the more likely culprit is.
This table makes the whole thing pretty clear. We start in the first column with our prior probability. That's what we believe before we find the bad part. We know supplier 1 gives us 65% of our parts. Then comes the conditional probability. This is our new evidence. We know from past data that supplier 1 has a 2% defect rate, while supplier 2 is worse, at 5%. We multiply those two columns together to get the joint probability. Then, for the final step, we just adjust those numbers a bit to get our updated belief, the posterior probability.
And boom, there's our answer. Look at that. Even though we get way more of our parts from supplier 1, the minute we learn a part is defective, it's now more likely to have come from supplier 2, a 57% chance. We've just used new evidence to logically update our initial belief. That's Bayes' theorem in a nutshell.
So, what's the big takeaway here? First, remember that probability is just a way to put a number on uncertainty. Second, you always have to start by counting your outcomes correctly. Third, don't forget to use past data to help you predict the future. Fourth, always consider that events might be connected. And finally, when you learn something new, use it to update your beliefs in a logical way. It's a whole framework for thinking more clearly.
So, whether you're trying to figure out if a project will hit its deadline or you're deciding on a big investment, you now have the tools to go beyond just a gut feeling and start moving toward calculated confidence. You can actually measure uncertainty. So the only question left is, what uncertain part of your world are you going to measure first? Thanks for joining me.